Xin phép của thầy là chúng ta bắt đầu luôn. Thì nhờ Huân là cắt cái mức của cả nhóm nhé. Nhóm này trừ cái báo cáo viên. Thế thì xin phép các thầy và các anh chị trong group thì là hôm nay chúng ta có một bài trình bày seminar. Thì về nguyên tắc là sẽ trình bày bằng tiếng Anh. Nhưng mà trong hôm nay ở đây là cũng chưa có người nước ngoài. Nên là trước hết là xin phép giới thiệu qua bằng tiếng Việt trước. Thì sau đó thì là tí nữa thì là Đông cũng sẽ trình bày bằng tiếng Anh, là một cái bước để chúng ta chuẩn bị làm việc trong cái sắp tới. Thì sau đó thì trong vòng 45 phút thì Đông sẽ trình bày, và đến lúc sau đó có độ 30 phút để nghe và hỏi đáp một số cái phần liên quan đến cái mô hình của cái bài báo. Thế thì xin giới thiệu qua với nhóm một chút về cái nội dung của cái bài hôm nay. Thế thì trong cái buổi hôm nay chúng ta nghe cái báo cáo viên ấy, báo cáo viên là đến từ bên trường Đại học Sư phạm Hà Nội 2, là Nguyễn Phương Đông, và Đông trình bày một cái bài báo mới được công bố trên tạp chí là FS, tức là tạp chí đầu ngành trong ngành MM. Thế thì cái tiêu đề của cái bài trình bày liên quan đến một cái mô hình mà phát điện các cái phát tán của virus máy tính, sử dụng cái mô hình mà lan truyền dịch bệnh SIQR trên mạng cảm biến 000 giây rồi theo cái mô hình Copernicus ấy. Ở đây thì là cái nghiên cứu này thì cũng đã được nhóm nghiên cứu cùng có cả thầy Hoàng Việt Long và thầy Nguyễn Long Giang là bên viện Hàn Lâm thì cũng đã hướng dẫn cho chỗ Đông cũng đã làm trong thời gian vừa qua, và trong cái nhóm cũng đã đề nghị chỗ Đông đã trình bày qua một số các cái phần cơ bản về cái mô hình này, cũng như là các cái ý tưởng chính liên quan đến việc mở rộng mô hình này cho một số các bài toán, và đặc biệt là bài toán về lan truyền dịch bệnh trong cái mô hình virus máy tính, và đâu đó có thể là mở rộng ra cho các cái mô hình về dịch bệnh như COVID-19. Thế thì sau cái buổi bài trình bày hôm nay thì nếu như bất kỳ thầy cô nào có câu hỏi liên quan đến cái nội dung bài trình bày ấy, thì xin phép là ghi vào trong cái ô thảo luận trong cái màn hình. Sau đó thì hết cái phần trình bày chúng ta sẽ trao đổi trên các cái câu hỏi đó. Thế thì xin phép là ngắn gọn qua một số thông tin cái bài trình bày của Đông. Thế thì sau đây xin phép là mời Đông trình bày trong vòng 45 phút cái bài báo, cái phần liên quan đến cái mô hình phát tán trên mạng cảm biến không dây trong vòng 45 phút, trình bày bằng tiếng Anh. Và xin mời Đông. Đông một tiếng Đông ơi.
Hello. Hi everyone. I would like to thank Prof and our seminar for giving me a chance to present my works in our seminar. The title of my presentation is the fuzzy fractional SIQR model for computer virus propagations in wireless sensor network using computer antenna band derivatives. This work is joined with Prof. Hoàng Việt Long and Prof. Nguyễn Giang. In this talk, I'll aim to discuss the attacking behavior of computer virus in a type of cyber environments with uncertainty parameters by using fractional differential equation. Our talks is organized as follows. There are 6 parts. In the first part, we give the problem formulation, and then we give the motivation of the problem. The main epidemic model we consider is the SIQR epidemic model. Then a keyword and my research is about the fractional dynamical system and fuzzy fractional dynamical system. In the fifth part of our presentation, I give some alternative result of my work. It's about the formulation of fractional fuzzy fractional models the theoretical result of the solvability of pro models, and the numerical solution of the models. The plastics is used for appendix and some reference. We turn to the first part. In our works, in order to investigate the attacking behaviors of malicious objects in various tensor networks with uncertainty, we construct fuzzy fractional differential models that describe the transmission of malicious objects along with the transmitting data process and analyze the property of the proper models. Our proposed model can be given in following general formulations. We can see at the formula 1. Here, this notation denotes for the fractional address of chain of the state vector x, and the notation x0 is initial data, with f denotes for given vector value functions. We our research in our research we try to model describe the models by differential equation models. Our investigations consist of two main approaches. The first approach is the main of the presentation today. The investigation of the proper models in sense of fuzzy fractional differential equation. Here it means we use a fuzzy parameter, fuzzy input, fuzzy operation, and fuzzy value functions. Thus, and when we give a fuzzy output, it means we consider a mathematical models that's required to use background of fuzzy analysis and construct necessary mathematical property criteria for investigate the property of models. The second approach, that's this approach I carry out, and I hope that we'll have some interesting result on the second approach. Is constructing the fractional differential equation that models the attacking behavior of malicious objects in various tensor network. Here, the input data is real value, but the setting of our program models is based on fuzzy rules. And I think that this approach is an interesting approach that can be near to the real-life models. In this talk, I will present the first approach. That is the main result of our approach. Now we consider the motivation of this work. Recently, wireless tensor networks have received an intensive attention due to the great potential in civil and military applications, such as the supervision of the transportation of pollutant, industrial monitoring, military target tracking, disaster recovery, biological detection, semantic sensing, and health monitoring. Here we can see that a sensor field, that's the number of sensor nodes, and it's and one is and it's used to capture and target, then and collecting the data from target, then it transmits data to the user via some device. Nowadays, along with the rapid spread of the internet and wireless sensor networks, the threat from the spread of malicious objects has also been increasing. Moreover, due to the restriction of memory resource of sensor networks and disadvantage in the location of the sensor fields, wireless sensor networks often have a weak defense and become untrusted targets of malicious objects. So, that means that no antivirus software can detect and clear all kinds of malicious objects, and the development of antivirus software in turn always lags behind that of them. Hence, there is a need to understand the feature and the characteristics of the propagation of malicious objects, and then we need to predict evolutionary direction, or need to be control the spread of malicious objects, just to minimize the influence of the virus attacking behavior. Beyond the similarity between the spread of disease in pollution and the spread of malicious objects in various sensor networks, some epidemic models have been applied to model and study the spread of malicious objects in various sensor networks. The mathematical model of malicious object transmission has been approached by a number of researchers with variety of models over past decades. For example, in the literature 2023, Mishra and Shani proposed a delayed SIRS epidemic model to study the spread of malicious objects in computer network and stability of malicious object-free equilibrium points. In the literature 24, model, namely SIRSV, are used to describe the dynamics of transmission with respect to time and will investigate the relation between the basis reproduction numbers of the models. Some other works, such as the predator-prey model, were proposed and analyze the energy conservation in context of worm attacks in wireless sensor network. And this research it also determines the condition for the stability of the different equilibrium points. The problem to investigating the stability of equilibrium points of the epidemic model is an important problem when we consider the epidemic models. At the 30 researchers, the author string as our study a fractional epidemics model for the spread of computer virus and discuss the influence of the dynamical behavior of virus transmission with arbitrary models, with arbitrary orders. Here, arbitrary model means that the rate of change in the model considered not at the first order, but with the beta belong to the open interval O1. Now I will introduce my models. The model is here. The notation SIQR are denoted by the density of susceptible infectious quarantine, and recovered sensor nodes at the time t respectively. Here, the state S consists of unwired sensor network that has not been infected by any virus. However, these nodes are vulnerable to virus, and therefore they are called susceptible nodes. The second kind of nodes in the state I that have been infected by virus in wireless sensor network, and moreover they may infect to other nodes in state S when it's along with the transmitting data process. The third state is about the Q state. That consists of on wireless sensor network, wireless sensor nodes, which are quarantine from the node I, and these nodes are said to be quarantine nodes. The last type of nodes is the sensor network sensor nodes in the state R. Thus, in this test, the sensor nodes are clear of virus, and they are temporarily immune. However, these nodes then become susceptible towards the possible attacks of virus. Here we can see that a diagram that models the SIQR epidemic model, and we can see the interaction between 4 states. I will discuss more about the interaction between 4 states. Here we can see that the sensor node outside the wireless sensor network enter the network with address A, and the number of sensor network and the number of susceptible nodes decrease since the nodes are infected by virus with probability lambda I, unless the network with a rest mu. Hence, we can see that state S have amount of A increasing the number of sensor nodes, but the sensor nodes at the step S decrease from the infected virus from state I, and it's decrease with a rest mu in the natural the natural death rate of the sensor node. The second sensor node is eyes. In this test, it affects that virus sensor networks are infected sensor network. In this test, virus infect sensor networks, sensor nodes in this state is a state S, and transfer them into the infected state with a probability lambda I. Each infectious node then belong to one of 3 following cases. The first case, the infectious node left the wireless sensor network with a rest mu. The second case, under the action of detection programs, every infected node can isolate to the quarantine node with a rate of gamma. Finally, by antivirus program, its infected nodes become recovered with a rate nu. The third sensor node, the third state is about the state Q. In this state, the infectious node can be isolated with a rate gamma to become a quarantine node, and then we can see that the sensor node in the state Q can belong one of 3 following cases. The first, X quarantine node can be left the wireless sensor network with a rest mu, and it can release to become a recovered sensor node with a red eta. And cortical nodes can be released to susceptible sensor state with a red omegas by reinstalling the system. The last state in this state, the sensor nodes left the network with a red views, and its recovered node can become a susceptible node with a property sigma. For this model, we summarize the parameter and variable in the table 1, and with the meaning at the second column. In our works, we our aim is to investigate the uncertain dynamic behavior of the virus propagation is that of the model that's modeled by the following fuzzy fractional differential equation. Here we consider the system number 2 with a floor equation subject to the initial condition number 3. Here we have two keywords, fuzzy and fractional. Here the fuzzy relate to the parameter or relate to the input of model that come from estimate measurements. We see that the fuzzy initial condition and fuzzy parameter for the model natural because we see that on real world model can always contain a certain factor, and there often a need to there often a considerable degree of uncertainty when we model, we solve, and we interpret the problem in the natural environment. In addition, rather than the particle values, we may have some, we have only imprecise or an incomplete information about the variable, about the parameter due to the applying different operating condition or due to the errors in measurement and computation. Hence, we see that the dynamical with fuzzy data, or in other words, the fuzzy differential equation here can appear as a natural way to model the propagation of the real-world process. The second keyword here is fractional. The fractional related to the rate of change in the model. In classical model, we often consider a model with first order or second order. In general, we consider a model with integral order derivative. But in our investigation, we consider the problem with the rate of change in a sense of fractional orders. Here we have the statement fractional dynamical system and fuzzy fractional dynamical system. First, the fractional derivative is considered as an effective tool to describe the memory phenomena. Here's the Keckner function of fractional derivative that is a characteristic feature of the fractional derivative. The Keckner function is connected memory function And there are many kinds of kidney functions. Its physical phenomena can be better modeled by a different type of kidney functions. For example, in order to express the property of viscoelastic material with memories in Kevin model or Weiss model or Maxwell model, they propose to use a non-singular kidney function of the form T minus S on over n4, where n4 is a number between 0 and 1. While in the case of expressing the decay physical process, the singular kidney function of the form e to the power of t to s on over n4 or the meter function with two parameters n4 b2 were suggested. Alongside with the development of fractional calculus, fractional differential equation, and fractional partial differential equation have been also dramatic studies with the high applicabilities. We can see this is application in a list of literature in the reference. Here we list some notable results, such as in the first literature, Akawan investigates the Cauchy problems for fuzzy fractional equation, in which the proper fuzzy fractional differential equation was studied without using fuzzy fractional derivative. In the literature force, Alavidaru investigates the initial value problem for fuzzy fractional differential equation with the yield of the fractional derivative inside the Riemann needle wind. In some recent literature, Long et al. Studies the local and non-local problem for fuzzy fractional partial differential equation under the capital GS differentiability. You can see at the 20 and 2021 21st literatures. And there are several literatures that consider fractional epidemic model and their application in computer network and wireless sensor network, such as in the research of Asuna, Huos, Zhao, and String. Thus, this researcher proves that our research can be applied for fractional order derivative. In this work, we consider a special type of fractional order derivative that have a non-singular kernel. In particular, in the 13 literature, the capital and Fabrizio has suggested an alternative concept of fractional calculus with non-singular kernel by using the exponential decay as a kernel. The new as a concept of fractional differential equation with non-singular kernel is proposed of Atangana and Baleanu, that's shown in the 6th literature. A new concept of Atangana-Baleanu fractional calculus are expected to better modeling the effects of memories in complex physical systems and recently this type of fractional calculus has achieved a loss of noticeable results, such as in the 7 literature of Atangana, the 18 with the application in the models dynamics of hepatitis E virus, or some other work of CERN with the proposal of fuzzy fractional derivatives under the phrase differentiabilities. In the 10 in the literature of number 10, Atangana and Hamos construct a Lie class partial integral differential equation with beyond the mid-tabular functions and give some interesting results. Overlaps in the 27 literatures discuss an ecological system consists of a predator and two prey with use of the Atangana Balianu derivatives in computer science and derive some numerical result based on the Adam Basford method. In the field of engineering, Akatani used the capital Atangana Balianu's fractional derivatives to study the SIQR problem as SIQR model and gives a numerical streams for solving the proper models. Another works in the fractional derivative with singular kernel given in the work of Seth et al. Just compare three concepts of fractional derivatives: real capital fractional, and mid-tabular fractional time derivatives, and apply them to study the vector equation and give a numerical results for this model. Just on reference, on research proves that the investigation of fractional derivatives with non-singular model with non-singular orders. In other hands, we consider the fractional differential equation with Atangana Balianu capital fractional derivatives. An interesting problem and attracts more attention. Under this motivation, now I will present some tips obtained result in my work. The first obtained result in the formulation of fractional calculus in Atangana Balianu sense for the fuzzy Fourier function, because when we consider a new style of differentiation, especially in the fuzzy environments, we need to reconstruct on analytics property for the problem, because the fuzzy analysis in the first stage of development. So we, in order to use the family result in a differential equation for the fuzzy Fourier function, we need to reconstruct these result and prove that it is the result how is the case of fuzzy functions. In the first obtained results, we propose two concepts: Riemann-Liouville Atangana Balianu fractional integral and Atangana Balianu fractional derivative in capital ties. For simplicity, we will call the Atangana Balianu by AB. Here, in the definition 5.1, we give the formula of the capital AB fractional derivatives of order beta between O and 1, 0 and 1. Here the expression phi beta is called a normalization function that satisfies the condition phi at 0 equal to phi at 1 equal to 1. The notation f dash to it means that the general SIQR derivative of the fuzzy function f. Here we can see that it's quite different from the well-known derivative because the derivative of function f, the fractional derivative of function f is computed by as a combination of computed as a function of the derivative of the well-known derivative. This derivative is not computed at the time t, but it's also computed at the some time precisely. In the next result, we give the form of the parameter forms for the fractional derivative in AB capital sense. That's useful for the numerical representations. After give the derivation of derivative, we give the derivation of integrals. That's its name is Riemann-Liouville rectangular binomial fractional integral. That's is given in definition 5.2. And then at the remark 5.1, we discuss some special case of the fractional order beta. If beta equal to 0, the fractional integral of s equal to the function f. With beta equal to 1, the fractional equation fractional integral of f equal to the well-known integral. Hence, we can just the formulation of fractional integral are quite natural. And an important result on the fractional derivative and fractional integral is a relation between the derivative and integral. In the normal derivative and integral, we know the Newton-Leibniz formula. That means the integral of the derivative equal to the f at b minus f at a. And the similar results are also discussed for the fractional case. Here in the theorem 5.1, we can show the relation between the fractional derivative and fractional integral. That the fractional integral of fractional derivative equal to the difference of the f at t minus f at the 0 as an integer price. This result
xin lỗi chị Đông ơi.
Dạ.
Có phải sai?
Alo?
Có ai nói ở trong cái mic của Đông nhỉ?
Vì em đang ở quán này có hơi ồn.
Ở ngoài à?
I'm sorry because I am in coffee, so by noise. I will try to speak now. The second result is a theoretical result on the solvability of the proposed models. Here we consider the general formulation of the proposed models in the model is given in the formula 4. where the notation d beta x denotes for the fractional derivatives of state vector x and x0 and else are given and x0 initial function and f fuzzy vector value functions. An important result in this section is a given of the integral forms of force. Thus, play a key role in the numerical in constructing the numerical results, numerical strengths of the problems. Here, in term 5.2, we give the formula 5 and 6 to the formula for integral representation for the problem force. And the formula 5 and 6 useful for construct the numerical strengths. The theorem 5.3 concludes that for each initial condition, we also find at least one a solution of the problem, or we always determine the behavior of SIQR for each initial result for each initial condition x0. And an important result of this research is about the number solution for the model that gives that bring us to the behavior of the model. In order to construct the numerical strengths for the problems, we denote the vector x and vector x0, and we consider the problem 7. Here the function s can a vector value function that have 4 compartment f1, f2, f3, and f4. Then we can see that the formula 8 and 9 are given from the 7 and the formula 8 and s is constructed based on the assumption that the function x is different EGS differential equation in Taiwan, and the number and the formula 9 are constructed under assumption that the vector x is GS differential equation in type 2. Under the formula 8 and 9, we construct the numerical strengths for the problem 7. In particular, we consider a uniform grid P that's considered on point Tk equal to K8, with K varies from O to N, and S equal to T. S equal to T over N. That's called S is called the length of partitions. Then for each N equal to O1, 2, we denote x minus n for n equal to x minus n for stn, and similarly s plus n for n equal to x minus n for tn. Then we determine the term x minus n for n plus 1 and x minus n for n plus 1 from the equation 10 and 11. Here we can see that at the expression of 10 and 11, there are expression Tn minus 1 Tn plus 1 plus tau on over beta minus 1 plus f tau and xn for minus tau. We will estimate the integers on the right hand side of 10 and 11 by using a two-step Lagrange interpolation polynomial. Thus, we will approximate the expression of f by a second by a first order polynomials. Then we substitute this estimation into the equation 10 and 11 and give numerical terms for the problem 7 that's given in the formula 12 and 13. Here there are two parameter C beta Kn and C bar beta Kn determined as follows. For this numerical term, we can construct the numerical solution for the problem and can plot it and can illustrate the term by plot some graph of the problems. Unnoticeable, uninteresting, important problem when we numerical choice a problem is compute the errors of the estimations. In remark 5.2, we by some fundamental computation we receive the estimation of our numerical terms is given in the following slide. Here we can see that the error bounds for our purple numerical terms is order beta plus 2. That is similar to the result in the 33 literature, and it shows a faster conversion rate with the result in the 17. Because in the 17 the conversion rate is order 1. So we can see that the numerical term quite good. In the last session appendix for some preliminary the result about the quasi function, and the last is about the list of preference of the results. The literature 23 and 17. Literature 17. The result of Benanu and Zaramin. That's all. I thank you for your attention.
So thank you so much for your presentation. Now we turn to questions. Are there any questions for the Okay, so I have the first question. So in the meantime, we're waiting for the other some questions. I have the first question. So can you Turn back to table one. Table one. Table one.
Trong ngàn anh như giáo mà
So I think I see that there are so many here. I see that they are S. However, they cannot express in new capital derivative in 5.1. 5.1.
Sorry, Professor. Because the connection are unstable, so I cannot hear the questions.
Let me write the question in the chat box. I just write the question in a chat box.
Yes. Thank you.
Chạy cá sấu ông gì nhỉ? Chắc là một gì nhỉ? Nó còn lại và nó làm việc mới làm đúng không? Đấy. Làm quế là có cái con chạy cao là nhảy. Bố về đây bố là bố về đây người đó là hai cái con nó lại. Em hỏi ông nào nhá.
Thank group sons the question. This parameter appears as the formula 2. As diffusion 5.1. At the diffusion 5.1 is a formula of the derivative, fractional derivative. Is not related to the parameter in the table 1. The parameter in table.
I'm sorry, but can you show the question in the chat box? Can you show the question in the chat box for everyone to see?
Yes.
Show the question in the chat.
Can you see the chat box?
No.
Can you see the chat box?
No.
Về nó làm cặp cân ngay quay qua hồng lại ba giờ đang nóng chụp thế đấy có làm ở trên đầu hồi lại đi lên này ngay chúng ta thằng
Question, can you see the chat box?
No. Now we can see the chat box. Please show us your chat box of the question.
Đấy, em đi sắp luôn trong ngày này có làm cái đấy.
I wonder why you cannot see the chat box.
Đâu làm có bài Honda đấy.
Mr. Long, can you see the chat box?
Biết đứa chị gà sợ mày nghe đéo là biết đứa chị gà nhà anh đúng rồi, cái loại sợ nói không phải quên.
I can see chat box myself.
Yes.
Can you click a chat at the most of Maybe alternate 8. Let's alternate it.
Và lên triệu nên được tiền không? Được tiền. Con này bị lột. Đây. Em mù mấy chục hectare cái cây.
Không có đồng.
Yeah.
Can you hear? Can you move? Can you move the other place? Because at the side is very noisy.
Yes. Because I am at a coffee, so
maybe other table.
yeah, yes.
Select other table.
Oh, at the outside there are noisier.
That is better.
It's not
Yeah, it's much better than before.
Mr. Tuấn, can you see the message of the Mr. Sơn?
Yeah.
I do. Yes. Mr. Sơn, can you see the chat box?
No.
Oh. The question of Peterson in table 1, there are so many parameters, 8 parameters. However, they are not expressed in the proposed capital derivatives in division 5.1. In the table 1, the S parameter are used for the, I think that's it, used for the proposed models. The S parameter are used for the model, the formula 2, the model in the formula 2. At the definition 5.1 is used for define the fractional derivatives, and I think that is don't relate to the Z parameters. I see. Yes. The parameter beta in the division 5.1 are different from the parameter in the table 1. Sorry, beta in the division 5.1 different from the parameter in the table 1.
Cái gì? Chuyển ra.
So the parameter beta is different from the SIQR model.
Yes, I see the questions. For sub function f1, f2, f3, and f4 are the function of the variables SIQR, as we show in models. The function f1 is respective to the first equation of the formula 2. f2 is a second equation of is the right hand side of the second equation, and F3, F4 are the right hand side of the third and the fourth equations. In section 5.3, in the proposed in the numerical terms, we give the general formulation f and the parameter and the in section 5.3 we consider this as the general formulation, and we don't present the C parameter in the section 5.3 for the simple models.
So could you please 5.3 section
5.3, yes. Yeah.
I'm sorry that I hear your answer. I cannot hear the answers from my second question. So could you please explain again?
Yes. At the problem 7, the function f is a vector value function with 4 compartments: f1, f2, f3, and f4, and the f1 is equation of the 4 variables s, I, q, r, and the f1 have the expression given in the right hand side of the equation of the system 2. F1 have the right hand side equal to right hand side of the system 2, and in the expression of F1 they contain the parameter and the variables. And F2 equal to the second right hand side of second equation of the 2, and the expression of F2 is also contain the variables si and the 4 parameters.
Ông nào mà nói chuyện?
Yeah, I understand. So the parameters of the SIQR model is embedded in equation 2, right?
Yeah. Yes. Yes.
Okay. So measure imitation of your model is so many parameters. So many parameters.
Yes.
So I think if we implement the model in realities, because too many So I have a first question.
Yes. The meaning of the end forecast in the SIQR. Yes. We consider the system 2 in the sense of a differential equation with the values which take values in the fuzzy environment. Thus, X function SIQR their value are not real values but fuzzy value, and for fuzzy numbers, in order to charge in order to express a fuzzy number, the FCAS is a let me turn to the appendix. Each fuzzy numbers can characterized by its FCAS, and its FCAS can be known as an interval of real life. So, in order to determine the expression of a fuzzy function, we need to present the function via its parameter form or via its FCAS forms. So for the SIQR models, it's a model whose variable take value at the fuzzy environment. So in order to present the behavior of the model, we need to present the system via its parametric form or via FCAS forms. I think that.
Yeah, I see. Okay, so anybody have a question for the presenter?
Điều gì?
Excuse me.
Chia sẻ cái cho bo con anh không?
Không?
Yeah, need to turn.
Chia sẻ cái gì?
So anybody have a question for a presenter?
Hello.
Hello.
Can you hear me?
Yeah.
I am Ramazani, and glad to attend your meeting. Actually, I was late, so please accept my apologies. I have a question about as I well understood, the presenter deal with the problem with the concepts of GH differentiability.
Yes.
Yes. You know, as I know, for solving fuzzy differential equations based on the GH differentiability, you have used the characterization theorem. So there are some forms for the GH differentiability, first form and second form, based on the number of the derivatives exist in the differential equations. Here, there are a system of first order differential equations, and as I see, there are 4 differential equations. So for each of differential equation, you have 2 options, the first form and second form of the GH differentiability. So there are 2 to the power of 4 ways for solving and obtaining the solutions.
Yes.
My question is that based on which assumption you obtain the solution, because there are so many solutions, more than one solutions, and actually possibly there are 2 to the power of 4 solutions for the system of differential equations that you have considered in your thesis. So my question is that which of them is the correct solution, and based on which assumption you choose that solution?
Yeah. So firstly, thanks to the Meran, for so much for your very interesting question. So, Meran, could you please show the picture? Your picture.
Okay. Sorry, because
yeah.
Oh,
it's nice to meet you. Nice to meet you.
Thank you. Me too.
Yeah, nice to meet you. I'm happy to have you here. Yeah.
Oh, me too.
Yeah. So
thank you for the invitation.
Yeah. So I'm looking forward for your next presentation in Wednesday. And yeah. So today we have a presentation from one of our research team. Yeah. And I think that is very closely to your research. Okay.
Yes.
Yeah, so I hope that in the seminar today we will also have the attended the Professor Long. Professor Long is in your friend?
Yeah. Professor Long, close friend.
Yeah, close friend. Okay. Okay. Thank you so much. So, do you understand the question of the Dr. Mehan?
I think that's the question of Dr. Meran about the under which assumption the problem falls has solution and what kind of solution is right, Dr. Meran?
Yes, actually, I mean, how do you solve the fuzz differential equation? Because when you start to solve fuzz differential equation, could you please go to the slide of your model, the SIR model? Could you go to that slide, the system of differential equations?
Yes. Okay. Is this model?
Yes, here. You know, so S of t, I of t, Q of t, and R of t. You have a system of differential equations of fractional order. So for solving such differential equations, you consider the concept of the derivative as the GH derivative. There are two ways for solving. The first way, based on the fuzzy standard interval arithmetic, the first way is that you solve such a differential equations directly. That is very hard and complex. But the second way that happens in the literature is that you consider, for example, the derivative of, for example, S of t as the first form of the GH differentiability, and for example, for I of t as a second form, and there are two options for each of these functions. For example, S of t can be considered as a first form or as a second form. So for each of these differential equations, there are two options. You have 4 differential equations. So there are possibly 2 to the power of 4 ways for obtaining the solutions. And with high probability, you will have more than 1 solutions.
Yes.
So which of them is the correct solution? And based on which assumption you have obtained the solution? Did you obtain more than 1 solution?
Yes. Yeah. When I simulate the example, in order to illustrate for the models, I will choose the range t, the interval OT, and choose the parameter t. For that, in this interval, our system have one type of differentiability. I need to choose t very small to obtain all solutions have the same type of differentiability. If we consider the case of GS differentiability,
no, I mean how many solutions have you obtained by solving such a differential equations?
We under assumption that in the interval OT they have no Swiss point of the functions. Then x variable has can be belong to one of two type of differentiability. So the number of solution is about there are 16 cases can occur when we consider on type of GS differentiabilities.
So you have obtained more than one solution, yes?
Yes.
So which of them is correct? You know, a differential equation should reflect what happens in the reality, and a physical system only have one solution. For example, you can consider a DC motor. When you turn on a DC motor, the angle of the shaft or the speed of the motor at any time has a unique trajectory. So a physical system, actually by mathematics, we are going to reflect what happens in the reality, in the physical system. So
yes.
Here you have obtained, and possibly and with high probability you will obtain more than one solution. So which of them is reflecting what happens in the real world? Based on which assumption? Based on what is your claim to choose one of them? And the other question is that, are you allowed to choose the solution? You know, we don't know what is happening in the reality. That's why we are solving a fuzzy differential equations. If we know, if we knew the solutions, so if we knew that, for example, after 2 hours, if we knew that after 2 hours what is happening in the reality, so we didn't need to solve the differential equations. A differential equation is a model of a physical systems or a dynamical systems in a closed form. And we are solving a differential equations to predict the behavior of the dynamical systems in any desired time. So you have obtained more than one solutions. So my opinion is that you are not allowed to choose the solution, because the solution of a differential equation should be unique. So how do you claim that these differential equations by your approach is reliable to be referred for the predictions? For example, if you have more than one solution, so I ask you that how much is S of t at, for example, t is equal to 5, and you answer me with more than one solution. So in this way, are you predicting the behavior of a system?
Yeah,
Yes.
So I also have some similar comment to ask you, because this model is in order to apply this model to reality. So we have a very unique solutions for that, but I'm not sure this is the warranty the unique for the system. But this question, may I ask Professor Long? Professor Long, can you explain some things for the question of the raised by Dr. Mehan? Professor Long?
Yes, yes, I'm here. Can you hear me?
Yeah,
Yeah.
yeah, I can hear you. I can hear you very well.
Hi, Mazan.
Oh, hi. Hi, Long. How are you?
Let me introduce something about you with my colleagues.
Okay.
Mazan Dazani is the doctor of electrical engineering from Iran. Now he is working postdoc in China. He's interested he's interesting in granular computing and next gen fuzzy inference system. As we know, Mazan has introduced some new concept of fuzzy theology. For example, granular derivative. Granular derivative. We have some extend paper from his concept and published in some good journal. Recently, he introduced new generation of fuzzy fractional inference system and public some paper in the TFS transaction of fuzzy system. Now I have some comment with Mazandani and our colleagues. As you know, because the FSS the Danos accept any paper, we use a NAS derivative except for generalized SIQR Z8 derivative. So we have to study this kind of model based on generalized SIQR Z8 derivative. If we want to publish in fuzzy set and system, although we know that there are many drawbacks by using this concept. One of the most drawback is that the consider model may have than one solution, as Mazan said before. Actually, to show the problem, we have to put many strict conditions on the problem. For example, we have to suppose that on the consider interval, we don't have any switching point, and the behavior of function does not change the sign in the consider interval. For this condition, the problem maybe have two solutions. One we call that the Taiwan solution, and the other is the Tai2 solution. The Taiwan solution, the bound of five solution maybe this asymptotic to the zero line solution when the time tend to infinity, and the Tai2 solution maybe the diagram of a Fourier solution increase by time, so that's the the behavior of Fuzzy solution may not reach the real solution, and actually it is not easy to consider that which is suitable or solution for the real for the exact solution of the model, and if we I think that if you want to consider which is a suitable solution of the zero model, we have to do some more tests. Maybe we test some point of solution, test some point solution, and with the we may estimate the distance or the exhaust between the Fourier solution with the real solution. One of the method is that we can estimate the errors between Fourier solution when we take the level with f cut equal to 1. Well f cut equal to 1, the fuzzy solution may be the real solution, and we have the script solution when f cut equal to 1, and then we manipulation this solution into the equation and try to test if it satisfy on the condition of the model.
Yes. Actually, in so many solutions that may be obtained based on this approach, especially about this model, we have probably more than one solutions. I mean, maybe 8 or 10 solutions, and for the alpha cut is equal to 1. Still, there are so many solutions that their core in each time is equal to each other, but their fuzziness is different. So I think we have not any measure or metric or any good criteria to choose from each of these solutions. Another, there's so many other challenges that are coming with this methodology. Actually, for example, if we consider in this model, there are so many parameters as for example, parameters and coefficients. And if the coefficients are fuzzy numbers, the other drawbacks of this methodology is that you can't factorize, you can't make any factorization in this model. For example, you can see in the second differential equations that the fractional derivative of I of t is equal to lambda multiplied by s of t I of t minus the second term. In the second term, as you see, there are 3 terms that have been added to each other multiplied by I of t. My question is that if you factorize the I of t in the second differential equations, is the solutions obtained again are the same as the before? The answer is not. Actually, if in the second differential equations, if you factorize the I of t, your solution again is different. So you can assume, so in this way, you have 2 multiply 2 to the power of 4 solutions. It means you have 64 possibly solutions, 64 fuzzy solutions.
Yeah.
So you
But
can't make any factorization in the second differential equation. So how we can depend ourselves to a methodology that even we can't consider any factorization in the model.
Yeah, but up to now, if we use Z8 derivative to study fuzzy different equation, we have no way. We have no way to pass the switching point problem. I haven't seen any new advance in the computation of fuzzy different equation by using Z8 different equation, Z8 derivative. So I have one question for you. Have you ever studied one simple fuzzy different equation by comparison between Z8 derivative and GR derivative? Do you have any comparison?
Yes.
About the big, I mean in comparison between the qualitative solution.
Actually, in some of my papers, I compared the SGH derivative and GH derivative. For example, in the first paper in which the GR derivative has been emerged, I showed that in SUAZ problem that GH derivative we obtain the derivative of a function that is not that is not differentiable. So that example shows that
I suppose that
GH derivative is not reliable.
Okay. I suppose that one we study fuzzy different equation by Z8 derivative. We suppose that we have two solutions. And which solution? We suppose that.
But by GR derivative, you can always get only one solution.
Yeah, we have 2K.
Pardon?
I mean that we when we study fuzzy different in order to okay order to we have order to if other one we have only 1K. If we consider the other two, for example, pattern different equation, we have to divide into 2K.
By which concept? By GH derivative or GR derivative?
By Z8 derivative.
GR derivative?
Yeah, Z8 generalized QR.
But
generalized
general QR, yes.
We have two solutions.
Yes, by GH derivative, yes. You have more than one solution. Yes, you have more than one solution. And at the moment, this is a critical.
We suppose that we have two solutions. And
yes.
Now we study this equation by ZR derivative. We have only one solution.
Yeah,
understand?
That's right.
So your
yes,
ZR solution consists with which solution of Z8 derivative?
You know, actually, when we want to compare two methodologies, we should refer to the concepts that are behind on the methodology. By GH derivative, I gave an example in my paper that, for example, if we consider the f of x is equal to the absolute value of x, so the derivative of the function absolute x at x is equal to 0 is not exist. In the reality, if you consider any function, if you consider this function is not differentiable. So if you consider a coefficients on the behind of the absolute of x, and consider these coefficients as for example number about 0, so even now such a function is not differentiable. By the methodology that are based on the GH differentiability, it gives you a solution. It gives you the derivative of this function, and it suggests you that the derivative of this function is equal to the coefficients multiplied by this function. So what is the concept of a fuzzy set? The concept of a fuzzy set is equal to the possibility distribution. It means that it shows you the possibility of any value that may happen in the reality. When you obtain the derivative of the k multiplied by the absolute of x, the derivative of this function at x is equal to 0, the derivative of this function by GH derivative is equal to k, while k is a fuzzy number approximate 0. It means that if the derivative of this function can be, for example, 0.3, 0.5. That is, such a thing does not happen in the reality. So, while if you try to obtain the derivative of such a function by GR derivative, it says that it's not differentiable. So we compare two methodology. One of the methodology is not in accord with what happens in the reality, and the others is in accord more. We don't know it is really happens in the reality or not, but it is more in accordance with what happens in a physical systems, in a dynamical systems. What about the other methodology? We are sure about the events that happens or not happen in the reality. When by a methodology, we are sure that what things does not happen in the reality, but the methodology says that it happens. So the answer is clear that we shouldn't depend ourselves with that methodology.
So, Mehan, so thank you for your useful information. Because to your discussion, we understand more about the ecosystem, and we understand about the limitation of the system proposed by in equation 2
Yes.
and equation 3. So this is very useful for the author to improve the paper in the future. Okay.
Mm-hmm.
Yeah. So yes. So besides that, we also request attendee to have a question for the presenter, if possible.
Yes.
I also have the question, the last question here. The last question I raised in the chat box. So
Yeah.
I
Yes.
think, yeah, I see that the models in the equation two not consider social attribute. Like I just check very quickly for a paper in 2020 for dynamic ecosystem in IoT. So they consider social attribute like device propagation capability. So my concern is that so when we formalize the model in a wireless sensor network, there is
Yes.
no information of the sensor network embedded in the system. This is one of the major differences and weakness of the paper, because
Yes.
because we can embed to many kind of networks, not only the wireless sensor network. Okay, so can you explain more about that? Thank you.
Yes. Thank you, sir. Professors. As we in our investigation, I see that our investigation have two main approach. The first main approach is we consider the differential equation that the parameter or the condition the fuzzy values. So the proposed models become a fuzzy differential equations, and result a present trace, and we use the fuzzy differential equation to model a simple model of epidemic model in wireless sensor network, namely SIQR, and it seems that this model do have not close to the wireless sensor networks, but as we discussed in the second approach, we consider wireless sensor networks as a scale-free network models, and each network sensor has a certain degree of connectivity and a certain degree and certain type of acceptance. So in the second approach, we will consider epidemic models in the wireless sensor networks, in which we consider both the structure of the network and the connectivity degree of each sensor node. So I hope that the second approach will meet the needs in the 5 questions.
Yeah. Sorry, my suggestion is that we please come back to the table one.
Yes.
Here you can see that the 8 parameters. These parameters only about the SIQR model. But
yes.
my last question is refer to you can take more parameters which are closely related to the wireless sensor network here. Here to make the more reality, as suggested by many speaker, many attendees here, like Dr. Merhan and so on. Okay.
Yes. Thank you.
Yeah. Sorry, any question from the other attendee? This is a very useful and interesting presentations from the mid-dome. Yeah. So any question? So Professor Long, do you have any comments for this paper or this research? Professor Long?
Actually, this approach we have applied to some other model or to modify to model the COVID pandemics, and when Dong began to do the PhD, I set this problem for first approach to study some computer virus propagation in wireless network. Actually, in the real world, there are some other useful approach. See, for example, one of the other approach based on another model based on probability. For example, the paper you have introduced, they use probability model to investigate the propagation of virus in wireless network, and I suggest Dong in the next paper, in the next work, he will use fuzzy inference system to study the propagation of virus in wireless network. This approach is very useful. It's near it use some advanced technique of fuzzy logic and fuzzy computation, and we hope that our new approach will models behavior of the virus propagation close to the real world, and we can use some data from the real world data sets to illustrate by our model. That's the thesis of our study.
Thank you so much, Professor Long, for the very useful suggestion for the next step of your research. So we also have the very long presentations and Q&A from our seminar today. And before we ending the seminars, so I just ask all attendees again. So do you have any question or comments for cooperations with the author, Mr. Dong, Professor Long, and Professor Zhang for this kind of research? So anybody, you have any comments or cooperations initiative, please right here. So before we start here, Mr. Wan, can you give me a say permission? Mr. Wan? Mr. Wan, can you give me a share permission?
Excuse
Mr.
me?
Wan? Mr. Wan? Yeah, can you give me a share?
I will stop share. Mr. Sơn, can you share your screens?
Yeah. Okay, so thank you so much, Mr. Dong. So we give you a certificate for the presentation. For the presentations here, we give Mr. Dong for the participating in a seminar on our summit 2 days, and for the end, we thank you so much for all the attendees to attend the seminar, and we hope to have all of you in the next seminar on this Wednesday, on the Wednesday evening in 6 p.m. And the next speaker is Dr. Mehant here.
Yes.
So
yes.
we just welcome all the attendees to join his seminar, and we hope to to hear more from Dr. Mehans the next Wednesday. So thank you so much again
This
for
Wednesday, yes.
coming to the conference and seminars. Yeah, so thank you so much. We
Thank you so
stop
much.
here. Yeah.
Yeah, thank you so much.
Yeah, thank you.
Thank
Thank you
you.
very much.
See you again.
See you again.
Thank you,
Professor.
See you again.
Thank you. See you.
Thank you, Dr.
Bye.
Yes, see you again.
Bye.
Bye.
Bye bye everyone.
All right, take care.
Goodbye, everyone.